I'm actually a postdoctoral fellow at the Niels Bohr Institute in Copenhagen, but I have a bit of, I lived here and there. So I did my undergraduates in Milan, because my hometown is from a very small city next to the Alps. And then I moved to do my PhD in Sissa, Trieste. It's on the opposite side from the sea, from Venice. And after that, I moved to Tokyo, to Japan, no, Japan. And I lived there for a while. I went also to, I lived a bit in Okinawa, beautiful place. I met lots of Brazilian Japanese there. And then, a few years ago, I went to Copenhagen. And yeah, that's my name. That's also my Japanese name that I use when I have papers together with my Japanese collaborators. And my main interest is dynamics, and I will show you that dynamics actually involves a lot of things. And I did many things during my studies. So from stellar dynamics to galactic center science, so studying the motion of and the dynamics of stars and gas in the center of the galaxy, next to Sagittarius star. But lately, I've settled on few body problems. Yeah. And few body problems actually involves a lot of scenarios, lots of physics, lots of astrophysical phenomena, and it's actually nice to be in this school that joins gravitational waves and planets, because I actually do these things, exactly these things. So I do a bit of planets, exoplanets, although I'm trying to stop. And most of my time nowadays is spent on modeling formation of gravitational wave sources. But today, I'll talk about the least astrophysical stuff that I do, which relates to chaos and the gravitational three-body problem. Yeah, just to show how far-reaching dynamics can be, this is a couple of papers I'm working with collaborators, and they're completely different topics. So one is about explaining the age of photoevaporating protoplanetary disks in the Orion cluster or Ion cluster. And the other one is about migrating very dense short period planets. And they both involve some sort of dynamical interactions and three-body dynamics. And they might seem very different, but through the eyes of dynamics, they're very similar. And that's why I'm happy to model both scenarios. And there are plenty of applications besides planetary physics, stellar triples, star cluster evolution. So the gravitational three-body problem is really, especially nowadays with Gaia, with LIGO Virgo, is really becoming, and Kepler or TEFS, is becoming nowadays central again in astrophysics. But today we're going to forget all this and focus only on the mathematical problem as the founding fathers of physics intended. Because the gravitational three-body problem traces back to Newton. Of course, he solved the two-body problem. That's easy. It's integrable. It's analytical. And then in his book, Principia, he actually started deriving a sketch to solve the next n, three-body problem. And there are many mathematicians who strive to find solutions and apply a three-body problem to different scenarios. For example, the lunar problem, explaining the motion and the precession of the perigee of the moon around the Earth. And eventually, Poincaré comes in the late 19th century and wins a prize set by the king of Sweden at the time for the most biggest mathematical physics discovery, basically, we could translate nowadays, demonstrating that the three-body problem is not solvable in a mathematical sense, but because of chaos, because of extreme sensitivity to initial conditions that this problem poses. And his work paved the way to a lot of branches of mathematics and mathematical physics. So first of all, there are different kinds of triple systems, and I'm focusing on the non-hierarchical triples. So non-hierarchical triples is where the point masses, are more or less the same size, and there is no spatial hierarchy between them. For example, you are in a triple system right now because the moon and the Earth and the sun make a hierarchical triple system. And the moon is stable, so it's not going to go away. But if the moon keeps getting farther from the Earth, at some point, it will escape, will be captured by the tidal field of the sun, and then it will become a non-hierarchical problem. And that's inherently unstable. So we call this kind of setup, this kind of configuration of three masses, three-body encounters. And I'll show you one here that I evolved using my code. It's a very accurate embodied integrator. What you're seeing here is a binary coming from the left and a single coming from the right. This pure Newtonian physics, but it's not as easy to solve as you imagine, because it's chaotic. There are numerical accuracy it's very important. So because a very simple small error can propagate and become huge. So what you see here is how this kind of system evolves. It's quite chaotic, as you might see, and it's very difficult to predict what will be the next step based on a snapshot, for example. So you can see how it's difficult. Please.
When two particles meet there, is it a real effect that they are kind of slowing down?
No, it's only for dramatic effect. No, it's actually my code that runs a bit slower, but actually it uses a trick. So my code can actually model collisions because it uses a trick called regularization, but it's a topic for a different day. And it causes a bit of slowdown during collision. But I left it because it's, again, dramatic effect. So you may observe a bit of, classify a bit the motion of this problem. So you see there are some moments in which all the particles are in the box. They're interacting and exchanging angular momentum and velocity at the same time. And at some point here, for example, here, you see there is a temporary binary that is formed. And then a temporary single, they're recoiling, and then come back. Show you one last time. And then at the end, this kind of interaction ends with the formation of a binary and a single on a hyperbolic orbit. So when you see that they exit the box at the end, they're never going to meet because their bonding energy is positive at the point. So the center of mass of the binary and the single, they're never going to come back and meet. Yes. So given these observations, are there better ways to solve this problem other than brute force integration, which is the video I just showed you? So first of all, you have seen that, I tell you, trust me, every unstable triple has to decay into a binary single unbound pair. And there are some caveats. For example, I'm talking about the non-hierarchical problem again, because the moon is kind of stable if it doesn't go around. And also braids is a kind of another special solution to the three-body problem. I'll show you one here. This is, for example, the figure of 8, very famous, one of the first braid that was discovered by mathematicians. And this is a special solution. It's stable, so if you perturb the particles, they're going to stay there for a long time, and it's non-hierarchical. But again, this kind of special solution, mathematically speaking, have measure 0, and astrophysically speaking, they should not exist. So we'll just swipe this under the carpet. Although, maybe later, Douglas Agee, a mathematician, applied mathematician to stellar dynamics, actually calculated the probability of this configuration of stars to be found in the universe, and it's in between 1 in the galaxy and 1 in the universe. So it's very small. And as I told you earlier, this three-body problem can be classified in a succession of 2 microstates. One, where all particles are in the same, more or less the same distance, and they exchange energy, angular momentum wildly. The other one is excursions, where they're temporarily forming a triple, in a sense, it's an unstable triple. And then, once the single comes back, the interaction will resume. So these 2 states keep alternating. And so here comes the more maybe theoretical part and mathematically heavy. So there is a very nice way to leverage and take advantage of chaos to solve the three-body problem statistically. And the first time that I was explained this, I did not understand, actually. So my goal now is to go home and for you to go home later, of course, not now, but with an intuition of how these statistical theories work. And so I'll make use of the blackboard. Yeah. So the main idea is that chaos mixes and washes away memories of the system, except globally conserved quantities, so angular momentum and energy. You can imagine the phase space of the Triboli problem as a box, let's say. And so initially it might be here, but next step is here, next step is here, next step is here. At some point, the system will jump around the phase space and will populate it uniformly, okay? So eventually, we can say that the system is everywhere after enough time. What does it mean? Is that, and also, but the system is not, has finite time. At some point, it will decay. We can imagine as an atom decay. It will randomly, it will split and create a binary in a single. But this can happen any point in space. So what we do is to apply the ergodic principle. We take this time average, and we sample it. So let's say at some point, I open the box, this box, and I find the particle here. And I can just sample this, let's say, this point in space, and map it to final outcome states. And what does it mean? In statistical mechanics, this is called the microcanonical ensemble. And we just need to understand what is this volume, how to characterize this volume. And after we have this volume, we can actually predict statistically the outcome of interactions. And you know, you just need to put yourself at the end of the system, at the end of the thing that the system has decayed. So there is a binary here, and there is a single. And you have the canonical coordinates here. So let's say RB and velocity, B. And this other coordinate is the position and velocity of the single. And what is the volume? The volume is simply all these four canonical coordinates integrated over the available phase space. Okay, so it's basically D3RS, D3RB, D3VS, and D3VB. Okay, but this, of course, this space is singular. It explodes, and we have to take into account physical constraints. One physical constraint is given by conservation of energy, right? So we can put here a delta function. This is the total energy of the system. We know that that's conserved. So at the end, when the binary and the single are very far away, the binary will have a binding energy. The single will have also an ejection, an energy. So, and these two need to sum to the total energy. So E0 minus EB minus ES. You can imagine the same thing for angular momentum, same exact delta function. And then there is one last caveat, is that not all orbits are correlated, are causally connected. Because, for example, let's see if we are considering this binary here, and the single comes from this direction. So they never interacted in the past. So this orbit is not causally connected to an escape. And the way to obviate this is to add a boundary condition to the integral, which is we consider only singles that escape within a certain radius from the binary. So it's basically saying that if this is the path trajectory of the single, this is RP, the pericenter. So the pericenter needs to be less than k times the binary C major axis. So this is a bit of a flaw of the theory because it's arbitrary. We need to define this interaction radius. Okay, if you have questions, this is your time. Hope you have some physical intuition of how this theory works. But what boils in the end is that once you develop this integral, the integrand is our trivariate probability distribution that we can sample. And we can obtain statistical distributions of final outcome states. And by final outcome states, I mean, what's for example, the separation of this binary? What's the eccentricity? What's the ejection velocity? And there is also what's the direction it escaped from with respect to the total angular momentum. And here is an example. I take this horrible function you see there. It's actually analytical. You can sample it, Monte Carlo, and obtain these distributions. No, actually, this is not sample. This is really, I plotted this. I marginalized the integral in state major axis and eccentricity. Okay. So this works as long as the three-body problem is chaotic. As long as your binary, your phase space is all mixed, and your state of the triple can be flattened down to the whole phase space. And I will show you that actually it's not so. The three-body problem is not completely chaotic. And let's find the first definition of chaos. It's by Lyapunov. Actually, this is the brother of Lyapunov. I found out yesterday. I always took this presentation. He was a pianist. But I kept it. I think he looks better than the brother. Yeah, the brother is a bit scary. We'll go stay with the pianist. So what is chaos is exponential divergence in phase space. So if you take an initial condition, you perturb it, and you propagate both solutions, eventually they will diverge exponentially. The rate of this exponential divergence is the Lyapunov exponent, or the inverse is the Lyapunov time. Okay. So let's do a numerical experiment, as we say. Let's run a few simulations, like this, very simple, like the one I showed you in the box. We have a binary, separation, 5 AU. You make your units because the three-body problem is scale-free. And we fix all parameters but 2. So we have 2 degrees of freedom. One is the binary phase, okay? And the other one is the inclination of the binary with respect to the, well, no point in drawing, with respect to the single. And we also choose different masses. So it's likely unequal masses means that the particles are not really identical to each other. So we have some physical property that we can use to distinguish the particles. And so this is how it looks like if we were to run 1,000,000 simulations of this box, binary phase, binary inclination. Each dot here is a simulation, is the final outcome of the simulation. What is color-coded is which particle is ejected at the end. So the red one is the initially single particle, and it was also the least massive. And body 2 and 3 are originally members of the binary. So what can you guess from this plot, from this figure? First of all, it's nice and fractal. But you see, there are big islands of uniform color. What does it mean? It means that even if I move the initial condition by a lot, the three-body problem always has the same outcome. So in these big islands, the three-body problem is completely regular. There is a smooth mapping between initial conditions and final states. And if I were to plot, for example, what is the final separation as a color code, you will see a smooth gradient across these islands. Yes, please. So the white, you mean the white? So the white is holes, because it's actually holes. It's not dots. It's the white background, because this is not a uniform grid. It's sample, so there are some places where there is no point, which is white. Yeah. Yes. These lines, no, they're totally real, and I couldn't write it in the paper because it came out later. I call them reefs. So if these are islands, these are like coral reef around the island, and you see they repeat themselves because my intuition is that they're multiple of the binary periods. So if you go in this direction, the velocity of the return time of the single changes smoothly, and so you can, if you flip the binary, you will always come to the same, in multiples of the binary period, you will have similar outcomes, more or less. This is very hand-wavy, but yeah. And yeah, maybe you can see better here, probably. So what you see here is not the final outcome states, is the lifetime of the system. So how long does it take to break up? And as I told you, this time is finite, so the only thing we need to do is to just integrate it until it disintegrates. And you see that these islands, the regular islands, correspond to very short lifetimes. So these are prompt disintegration, prompt decays. So the single arrives and boom, breaks immediately. The triple breaks. Good. Any questions? I was waiting for a question. Yeah. Yes. It's extremely long lifetimes. Exactly, exactly, perfect. Yes. The reason is that the boundary between I say in a regular region, there is, as I said, there is a smooth mapping between initial conditions and final outcome states, including escape velocity of the single. So on the left, where the region is black, the escape velocity of the single is above the escape velocity. So let's say here, this is the threshold for this to become unbound. But then there is some direction in phase space that this velocity goes down, goes down, goes down, and at some point, the single will remain bound. But there is no limit how bound with how low the energy can be of this particle. So what you see here, these are extremely long excursions. Maybe this particle is traveling for a long time. Astrophysically speaking, might not make any sense. Maybe it's like it would go out of the galaxy. But at some point, it'll come back, because it's still bound. So that's why you have these extremely long lifetimes. Yes? Well, it's a discontinuity because so here is black. So for example, let's say this is for example, let's say is the x-axis, okay, the phase. Say if you stay there and you move, but the particle always escapes with the same speed, so it's still unbound. And at some point, suddenly, the velocity of this particle becomes low enough that it's actually bound. So it's below the escape speed. So this is the discontinuity. And you can see it exactly because there is the three-body problem is regular. So as you move across this axis, you get something extremely smooth. But then here, the particle will come back after a very long time, and then we'll resume the interaction. Did I answer your question? And so after we run these experiments, we can actually compare with the theory, right? I told you we have actually plenty of theories that have been developed since the 70s. Yeah, I forgot to say, the statistical escape theories was first developed by Monaghan, a statistical physicist. And the latest developments of this theory arrived to these years. So people are still working on this problem. And so if we measure what is the escape probability, which is a quantity that theory will give you, with the numerical experiments, we see that they're kind of at odds. And also, if we plot the distributions of final outcomes case, it's going to be off. So for example, yeah, you can see that the percentage of escapes in regards to mass species is completely wrong here. It's not very well predicted. And also, if I plot, so the theory is the dotted line, and you see there is no much difference between mass species in case of the eccentricity. But then if I plot the numerical results, you see the two distributions completely disagree with each other. It's completely wrong. But if I remove the regular interaction, so if I cut out of the plot, I cut out the islands, then we get much better agreement with the theory. And probably you don't see, because it's a bit too crowded, but the new distribution, without all the regular interactions, it actually lines quite well with the expected thermal distribution, a slightly thermal, almost thermal distribution. And also the percentages are extremely close to what we expect from theory. Okay, yeah. Then what I did was to do a different kind of experiments, because I saw that, well, these big islands are there, but what about the rest of the sea? Is it really chaotic, fully chaotic, or not? And what I did was to do some zoom in of the big plot into different region of the phase space, and zooming in until I ran out of numerical resolution, basically. And you see that it's a beautiful demonstration of the fractality of chaos. That the more you go in, maybe you see a region which is completely chaotic, but as you zoom, you start regularity emerging. And this is kind of expected in a sense, because chaos is fractal. But one thing is to actually visualize it and also measure it. And you see same exact patterns in when you plot the lifetime of the system. And yeah, so as a physicist, I don't really like to just look at figures and say, okay, yes, it's fractal, but I really wanted to measure it and quantify what's the fractality of chaos of the three-body problem. And if you're not familiar with the fractal dimension, is a way to quantify the filling factor of a fractal surface within an embedded space. Okay, and a very famous example is the Cantor set. If you take a segment, you remove the middle one, then you take the other one, you remove the, and then this is very mathematically well posed, and it has only one single fractal dimension. And you can also measure fractality empirically using, for example, box counting. I tried this, it completely fails because it's, we have limited, I was limited by resolution. So how many dots I put in the box, and also the box itself is a boundary. So eventually I went to use some sort of estimate for fractal dimension that is also used in cosmology. I found out later. It's called two-point correlation fractal dimension. And it's basically just counting the number of pairs you have between the points in your phase space. And what you see here is that if I do this experiment, the power, the slope of this curve gives you the fractal dimension. If I take all points, I obtain something close to 2, which is exactly the embedded space dimension. So something that is not fractal is going to have dimension 2. But something that is a bit fractal is going to have something less than 2. And the closer to 1, the more thin is the let's say, the more topology of the fractal surface. And yeah, it turns out that actually maps very well. This fractal index maps very well to the morphology of these islands and strips and reefs. Okay, yeah, I can. Oh, another very interesting effect that we could measure is the effect of numerical errors. So what I showed you so far is all made with simulations, brute force integration. But even the most accurate code has some limitation, and one is floating point accuracy. So we only have 64 bits in a number, and if we run out of accuracy, then that's it. Except that my collaborators brought arbitrary precision code that uses arbitrary length bits. And so we could rerun for the last zoom in using a much more accurate integrator. And what you see here is the difference. The top is my code. The bottom is this arbitrary precision integrator, which is extremely slow. And you see what is the effect of numerical errors is actually introducing a mixing in the phase space, which is completely artificial. And we named it numerical chaos. And so numerical errors actually introduce, they make a system that is actually regular, chaotic, but only apparently. And what you can see is like these stripes, these narrow stripes actually become very diffuse. And each individual simulation not many simulations in the above plot are actually accurate. But overall, statistically speaking, there is very little difference. If I take all if you make all of the statistics of how many particles escape in the red particle escape in the upper box and in the lower box, actually what you see is the numbers are basically the same up to 1%. And this I can skip this. Of course, since the three-body problem is scale-free, you can actually zoom in as much as you want. And if you set a physical scale, let's say these are black holes of 12 solar masses and separated AU distance, you can go up to a distance in initial position that is below the Planck length. And this is quite fun, thinking that you have some chaos, regularity and chaos below the Planck length, and how would that couple with whatever physics we have down there, microscopic physics? Okay. Now so everything I showed so far has very little to do with astrophysics, and I was actually very, very happy with that. I really intended this paper to be more mathematical physics, and I wanted to submit to Celestial Mechanics and Dynamical Astronomy, a journal that Silvio was editor a few years ago. But then a collaborator of mine, professor from the Netherlands, computational astrophysics, started, we should submit to an open access journal. I say, okay, Simon, I can submit to to A&A, astronomy and astrophysics, but it's going to be difficult. The editor is going to desk reject it because there's not much astrophysics. Say, but three-body problem is very important. They should not reject it. Okay. So I changed the format of the paper. But I knew it was going to be difficult to submit to A&A, so I wrote we say in Italian, to put your hands forward, wrote a cover letter to the editor saying, please, our paper is more mathematical, numerical, but this three-body problem is very important, has many astrophysical implications. A few days later, the editor replies to me, your paper is not enough astrophysical, but it looks interesting. Can you elaborate more on the astrophysical implications? So eventually, 24 hours later, I added a new section in the paper called Astrophysical Implications. You see, and if you look at the archive history, you can actually see a few days later, now we added astrophysics. But actually made the paper much better and much more easy to sell. And the main astrophysical implication is about gravitational waves. And why? Because we have seen that the distributions of outcome parameters in the regular phase space are very different, completely different. Especially, there is a huge peak at high eccentricity that is not present in the chaotic binaries, let's say. So, and you should know by now that the coalescence time of binaries has a steep dependence on the eccentricity. So the more eccentric is the binary, the shorter is the time to coalesce and produce a gravitational wave event. So what I did is to calculate what's the difference in coalescence timescale between a regular and chaotic binaries. So binaries that were formed through chaotic interactions and binaries that were formed through regular interactions. And turns out there is a huge difference. Like there are 3 times more binaries that coalesce in the regular region of phase space with respect to the chaotic region. And the fun thing is that actually many people use statistical theories to do fast predictions of gravitational wave population, including the former PhD advisor of Filippo here. And so actually this shows something that was not actually clear before, is that statistical theory are actually very, very helpful. They're very fast. You don't have to run expensive simulations. But of course, there is a trade-off that was not really clear up to now. And actually, if we apply and we use these theories to astrophysical scenarios, there might be something we are missing. And these are a bunch of codes that use this kind of approach that might be biased. And OK, with this, I finish. I think I showed you, let you read this. So one thing, maybe I'll just show a bit about what I'm trying to do now. It's very difficult once you get into chaos to come back to regularity. So you kind of get dragged in a lot of problems. And so what I would like to do is to find a theory, make non-statistical theory, a regular classical theory, to predict the regular region of the phase space. I tried this when I visited Edinburgh 1 year ago at a chaotic meeting with Douglas Agee, but so far what we produced doesn't really reproduce the numerical results. And another quite interesting, so all the simulation I've run, they are Newtonian. But of course, if I really want to say I'm modeling black holes, I should add post-Newtonian terms, which no problem, my code has. But it seems like that post-Newtonian corrections, so corrections to the equations of motion up to v over c squared, make the system less chaotic, so more regular. And this paper by, again, my collaborator showed this, but he actually does not explain why. So what I'm working with a collaborator here in Florence is to try to find a way, the reason why post-Newtonian terms are actually suppressing chaos. And it's very difficult because post-Newtonian terms are quite complicated, so you cannot really solve the variational equations. You have to take the Jacobian of these expressions. You can do it in the Newtonian case, but in the post-Newtonian it gets very, very tricky. And let me go back to the summary. Finish here. Thank you.
I have one question. You compare
Yes.
How the predictions were done?
So, oh, here. So there are two branches of statistical escape theories. So the one, yes. So what I use for distributions, I used this prediction by Stone and Lee. Is actually is a Nature paper on the three-body problem, and you see this expression. This is the trivariate distribution. This is a probability function of outcome states. So given I can sample or I can marginalize this distribution, and given energy, total angular momentum, and masses, of course, you can obtain probability of every quantity, of outcome quantity. And this is given this kind of statistical, it's called macrocanonical ensemble approach that was started many years ago by Monaghan. This other one is actually a bit different. Wait, this prediction here on the mass ratios. So what's the probability given a certain mass is slightly different. I use this new theory from Barak Cole. Is slightly more complicated. I don't fully capture the mathematics because it uses some techniques from string theory, which I haven't looked into. But it's kind of tries to solve basically this issue that you have an arbitrary interaction sphere. And so instead of defining a radius where you consider interactions or not, it uses kind of a regularization function based on how much chaotic is the interaction. The main issue is that we don't actually know what is the form of this function to regularize the phase space. And when I first wrote this draft, I actually wrote the theory is incomplete because we don't know the major form of a function that defines the theory. But then Barak wrote me back, the theory is complete. We just don't know the shape of this function. So I had to rephrase a bit.
For a conservative system, chaotic, non-integrable,
Yep.
the fact of having a prediction is very strange.
Yeah, but
Because the nature of the problem is unpredictable.
yeah, but we can.
How could
Yeah, but
that equation give a trustable prediction?
because it doesn't give a single prediction. It doesn't give a deterministic prediction. It gives a statistical one.
Can you go back to your slide about gravitational radiation?
Yes. Oh wait, here.
Put a microphone, please.
Yes, yeah.
Now, okay, better. All right, so I'm not sure if I know how to formulate this question, but so if you were to take a picture of the phase space, so by the ergodic theorem, you could say that each point there corresponds to some power of gravitational radiation, you could say, depending on the state of the system there, right? So if you were to color this by the amount of gravitational radiation that's being emitted, how would that look? Do you have any idea?
Yeah.
Of course, you know, knowing what, so you can only talk about an instantaneous amount of power in gravitational radiation, but, you know, it's, if you take a picture, then you use the ergodic theorem, you would also say this much is being emitted. Is it more by which kinds of systems? Do you have an idea?
So I'm thinking about two different aspects here. So one is with the ergodic theory, we have outcome probabilities, and then what I'm doing is to gauge what's the gravitational wave radiation emitted by the final binary. But what happened in the meanwhile, I'm not considering.
Yeah, if you consider like an infinite, a very large amount, a number of systems, they will be each one populating your phase space in the ways that you saw there, right?
Yeah.
So you can ask at one instant in time, what is the power that each point of those is emitting? right? You would have a different picture than the one that you showed there, right?
Exactly.
So it would be interesting to see if it's
Yeah,
totally dominated by the pairs which are stable and have close orbits, or if there's a large amount which is being emitted by something else, some other systems, like things which come very close by, but then they go away, right? What would that look like?
Yeah. So first of all, I would start to have mergers. So some simulations that do actually.
Yeah, without going into that.
Oh, okay, without going into that.
That's raising the bar too high.
Okay.
Anyway,
yeah,
it's just a provocation. I don't know if you have an answer.
No, I don't
have. It
have.
would be interesting to know.
So I have a related question. How does general relativity impacts when you integrate over the phase space? Because energy is not conserved anymore.
Yeah, exactly. So everything I showed you so far was purely Newtonian, because initially I really wanted to compare with the theory, which is Newtonian. And once you add a scale, first of all. So you break the scale-free invariance of gravity once you add the finite speed of light. And so this changes a lot. And also you need to have mergers because you cannot really integrate orbits below the Schwarzschild radius. Your post-Newtonian expansion breaks down. So you start to have mergers. The few studies so far, they show that the system becomes more regular. And you're focusing on the dissipative part, right? Dissipation, so let's say 2.5 post-Newtonian term. Mergers definitely are gonna regularize a bit more, makes your system a bit more regular. And
sorry, but in terms of conservation of energy, globally, of course, general relativity doesn't give you a conserved energy, but he's talking about a small closed system. So in that sense, there is conservation of energy. There is no conservation of energy for the universe, but there is conservation of energy for something like the box that is considering. It has to be, right?
But once you add the radiation.
No, but that's but then. Okay, but that's still energy. You can
it is conserving.
Sure, it's radiating away. No, but that's different from energy non-conservation, that there's no conservation of energy. Okay, so maybe you're talking about different things.
But
you're talking about the dissipation from emitting gravitational radiation.
I would say it's not. So you see that two particles really need to get very close to each other for gravitational wave to kick in. And generally, if two particles are unbound with respect to each other and gravitational wave is strong enough to kick in, they're also gonna merge, basically. No, there is. If you put them far away, if you make your scale large enough, then you are again in the Newtonian limit.
No, but that's fine. I mean, I guess you don't even have resolution enough to see the final in spiral phase, right? Where the back reaction from the emission of gravitational radiation really lowers the orbits and so on. But you can still calculate the gravitational radiation just in the regular orbit or even in close orbits with eccentricity and so on, right?
But for instance, orbits that would escape, they could actually go back.
Yes, in principle, but so the main issue is how steep is the radiation term with respect to distance, which means that to make an orbit bound, you can do it, but usually you're going to lose so much energy that it's going to merge very quickly. So the parameter space, given that you have a very steep dependence to the pericenter distance, you have a very narrow region of phase space where you lose energy, but just enough to still have a large orbit that's not going to merge quickly. Because you have a 10 to the minus 7.5 that's almost like the pericenter distance if you.
We have another question here.
Yes.
Thanks for a nice talk. How do your result depend on the specific choice of the initial masses?
Very good. That was also the referees that asked me to do more simulations about. So everything I showed you is in a very fixed configuration. And of course, things should change if you change the initial separation of the binary, or even simply you have a hyperbolic encounter rather than having a binary and a single, just let them go. And I did, oh, I forgot to add the slide, but maybe I have something later. Let me check. Be very quick. Yeah, too many slides for, this is it. Yeah, wait. Okay, yes, I did run some extra simulation using hyperbolic setup, and this is something I prepared a long time ago, but they all looked at this, basically in the appendix of the paper, and they show very similar patterns that I found in my specific setup of rest mass. So it's actually very general. It's not just the specific initial condition that I chose. I measured fraction of the regular phase space that goes from 28% to 84% in some cases. So there are, especially if your single is very fast, so the velocity at infinity of the single is very fast, what you're gonna have is flybys mostly. The binary and the single barely interact. So these are regular regions, right?
I'm sorry, but when you say phase space, you mean also that you change the initial mass?
No, I was thinking of phase space in terms of initial velocity, position. Masses, this is gonna change, yes. And yeah, and of course, you can think about the limit. So the more, let's say, the massless your one of the particle becomes, then the motion of the binary is gonna be regular, because it's not gonna be affected by the test particle. But the test particle motion will be chaotic. Then you basically separate the phase space. You kind of break it. This approach breaks down completely, because this considered that all coordinates are chaotic. And nobody has actually worked out something that could work in the mass regime. But as long as they're near equal, this approach works well.
How long does it take to run all the simulation you ran?
1 million simulation, couple of hours on 100 cores.
All right.
This simulation is, you did this in Denmark or whatever?
It's actually, this is a pandemic project of mine. So it's a project I started in 2020 when I was bored at home. And then I had to put it in a drawer until early this year that I finally got it back from the drawer and I started working on it. And I'm very happy that it finally got published, yeah. So Japan, I did it in Japan.
More questions?
Nice.
So you complain that fast code, like fast cluster.
Yes, the one of your supervisor, right?
It was also your supervisor. But
Yes, true.
So, but can your approach be useful for those kind of codes?
As long until me or somebody else finds a theory to wait, where it was, until somebody finds a way to predict the regular interactions, all you can do is run simulations. So again, I'm not against analytical theories, but there is a trade-off, and either we find a classical theory to compensate for these regular interactions that are not predicted by the chaotic theory. But then it's tricky because you have different phase, so the fraction of the phase space that is regular depends in a weird way on the initial conditions. So even if we find a theory for regular and a theory for chaotic, how do you know how to mix them? So I think it's a very difficult problem.
Do you really need a theory, or can you use machine learning?
Yeah, okay, machine learning. Yeah, that's interesting. Yeah.
So how do these codes scale with the number of particles? You're talking always about 3.
Yeah.
So is it that
Yeah.
Does
No,
it
it's-
scale with the number square,
so-
with the number to 12
So this
power?
is
what
no, it's O(n) squared. Yeah, because it's a direct embody, so you have to solve. What is this?
Okay, it's n square.
Yeah, you need to do the sum square,
All
all
the
the
pairs.
all the pairs. So mine is actually a few body code. It's not I mean, it is n body. I can run even thousands of particles. It's just gonna be slow, not just because the force, which is I could parallelize the force calculation. It's because also it does a extrapolation. So it runs. You know, when you have an embodied code, you usually have time step 1 equal time step the previous one plus some weird function of the acceleration at different time step. And my code plus delta t, or delta t. Mine does this, but then also decreases the delta t to get a different expression of y. Let me just write somewhere else. There. It's quite interesting. It's called Burlish-Story extrapolation. So this is, let's say, the time step. And first, you use a big time step. You get this result. Let's say this position of this particle. Then you make it half, and you get this position. It's slightly more accurate because your time step is lower. Then you still decrease it, and eventually you use a polynomial or a rational function interpolation, and you extrapolate to infinitesimal time step. So that's the slow part, besides the force calculation.
So you actually do it many times. For each
Yes.
time step, you're doing it several times.
Yes. And also, since it's like extrapolation, it's very difficult to do variational equations and
But that doesn't. I mean, that's not order n. This is
Yeah.
order n squared. There is already.
yeah. This is
So
and
in
also,
principle, you could solve for, instead of doing a million particles, a million simulations with three particles, you could do 1,000 with 30 particles or something.
yes,
like this.
exactly, yes, yeah.
Okay.
And
Do you use periodic boundary conditions or just open?
no,
boundary
open,
conditions?
open, yeah.
Okay, yeah, of course. 'Cause
Yeah,
it's
yeah,
an interaction.
And
Alright.
and also time is also an integrated variable. It's extended phase space, so it's a fictional time and a true time.
Okay. Any more questions? Well, if not, thanks, Alessandro.
Thanks.